So people here will basically do fundamental science in magnetism. They will use very high magnetic fields or very high pressures to study how materials change when you apply these pressures or magnetic fields in cold samples. So one of the examples of this is the high temperature superconductors, which are very functional materials. They work at high temperatures, superconductors that can work under liquid nitrogen temperatures in principle. And these materials are very complex and they're magnetic in nature. And what people will investigate is how these magnetic dynamics of the material change when you apply pressure. That's one of the things you can only do on BIFROST. Another thing you can only do on BIFROST is study how complex interaction between, for instance, magnetic properties and structural properties of materials, they actually function on a fundamental level. So if you are interested in these fundamental hybrid interactions, they can be studied usually at very low energy, and they also require very high resolution. So one of the things that BIFROST can do is ramp up the resolution so you can study complex functional materials at very low energy transfers. And some of these materials, they can be used in the IT sector. If you want to make next generation transistors, for instance, you usually use some of these functional materials. They're called multiferroics, and it's a general class of materials that you can investigate with this type of instrument. So we want to be as ready for neutrons as we can, and the next couple of months are going to be focused on that. So once we get neutrons, we'll go through a very stressful period of hot commissioning, where we will hurry up and make sure we understand the beamline. We understand all the subcomponents of the beamline and the neutron properties of the beamline, so to speak. How does the neutron scattering work on the beamline? Have we calibrated the flight path? And before we can do any science on the beamline, we need to make sure all these work as intended, and if they don't, we understand how or why. So there'll be a lot of iterations, there'll be a lot of fixing things in that period, because we'll discover obviously a lot of problems, because these instruments are prototypes basically, and this is understood. So we're going to spend the first 6 to 9 months figuring out all these problems. And once we're done with solving all these, we're ready to do the first test experiments where we put in scientifically known samples, where we know the physics of the sample, and then we remeasure this and compare it with literature. And once we can reproduce known results, we're ready to start ramping up the complexity in the science that we do. So we'll start with some fairly simple science cases where we just need the next step to have a valuable publication. And then we'll ramp up the challenge progressively, doing harder and harder experiments that require more and more resolution, more and more complex sample environment. And we'll do that in a stepwise process. And once we're ready to do the really hard experiments, we're ready to have the users.